To finish out this section, I've got a theorem that says there are an infinite number of prime numbers, and I have the proof there. And I want to focus, though, on these next two theorems. The first one says that if n is a composite number, so if n is not prime, then n has a prime factor p, for which p is less than or equal to the square root of n. So let me explain what this means. Let's say we are looking at the number 35. The square root of 35 is about 6. It's just under, but let's say it's about 6. This theorem says that 35 has a prime factor less than or equal to 6, and 35 is divisible by 5, which is a prime number. So there's the theorem in action. That's what this first theorem says. The second is a test for primality. If you want to check if a number is prime, because some numbers like 5 or 7 or 11, we automatically know those are prime numbers, but some larger numbers you're not going to recognize as prime numbers. So this is a test for them. What you do is you take the square root of the number in question, and then you list all of the prime factors less than that square root. If none of those numbers divides the number in question, then you can conclude that it is a prime number. Working through these types of problems, you might want to have a calculator handy, but I want to show you how exactly this is going to work. So we're going to determine if these four numbers are prime or composite. So 361, we're going to start there. The square root of 361 happens to be the number 19. And 19 is a prime number. Since 19 divides 361, 361 is composite. So remember, a prime number is only divisible by 1 in itself. In the case of 361, it's divisible by 19, thus it's composite. So now let's look at 1013. The square root of 1013 is about 32. So we're going to test the prime numbers less than 32. So that means we're going to test 2, 3, 5, 7, 11, 13. You can hopefully see why a calculator might be handy. 17, 19, 23, 29, and 31. Those are all of the prime numbers less than 32. If you test these out, again, this is where the calculator is handy. If you take 1013, divide it by 2, divide it by 3, and so on, you'll find that none of those numbers divide into 1013. So therefore, 1013 is prime. So again, since none of these divide 1013, it is prime. The third one is 4049. Same process. You take the square root of 4049, and it's about 64. So what you need to do is test the prime numbers less than 64. So this is an even longer list. It's going to be 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, we're going to keep going, there's more, 43, 47, 53, 59, and 61. There's a whole bunch of them. And if you divide 4049 by each of those numbers, you will find that none of them divide into 4049. It is a prime number. And I'm leaving out this phrase here. Since none of these divide 4049, it is prime. So 4049 is also prime. So for the last one, 6083, same process. You take the square root of 6083, and it's about 78. So you will test all of the prime numbers that are less than 78. So it's everything here and then a few more. It's also going to be 67, 71, and 73. It turns out that 7 and 11, they both divide into 6083. So 6083 is a composite number. But that walks you through the test for determining whether a number is prime or composite. You maybe can see that as the numbers get larger and larger, the test becomes a bit more cumbersome, and that's why mathematicians a lot of times will use computer programs when they're looking to see if these very, very, very large numbers are prime or composite. If you're working with elementary age children, you probably would not go much past 3 or 4 digits, and I don't even know how often you would get into 4 digits. But that is the test for prime and composite numbers.